What is deadlock? Beginner level. Introduction. Modern programs often run multiple tasks at the same time using techniques like multithreading, concurrency, parallel processing. These tasks may need to share resources such as files, memory, databases, network connections. Sometimes, two or more tasks wait for each other to release resources. When none of them can continue, the system gets stuck. This situation is called a deadlock. Deadlocks are common issues in multithreaded and concurrent programming. What is a deadlock? A deadlock occurs when two or more processes or threads are waiting for each other to release resources, and none of them can proceed. In simple words, deadlock equals a situation where tasks are stuck waiting for each other forever. When a deadlock occurs, the program cannot continue its execution. Simple example. Imagine two threads. Thread A holds resource 1. Thread B holds resource 2. Now, thread A waits for resource 2. Thread B waits for resource 1. Neither thread can continue. Both are stuck. This is a deadlock. Deadlock visualization. Example. Thread A. Down pointing arrow waits for resource 2. Up pointing arrow held by thread B. Thread B. Down pointing arrow waits for resource 1. Up pointing arrow held by thread A. Both threads wait forever. Example in programming. Example scenario. Lock 1. Acquire. Lock 2. Acquire. Another thread. Lock 2. Acquire. Lock 1. Acquire. What happens? Thread A locks lock 1. Thread B locks lock 2. Thread A waits for lock 2. Thread B waits for lock 1. Both threads wait forever means deadlock. The 4 conditions for deadlock. Deadlock occurs when 4 conditions happen simultaneously. 1. Mutual exclusion. Resources cannot be shared. Only one thread can use a resource at a time. 2. Hold and wait. A thread holds one resource while waiting for another. 3. No preemption. Resources cannot be forcibly taken away from a thread. 4. Circular wait. Threads form a circular chain waiting for each other. Example. Thread A means waits for thread B. Thread B means waits for thread C. Thread C means waits for thread A. This creates a deadlock cycle. Real-life analogy. Imagine a traffic intersection with 4 cars. Each car stops in the middle waiting for another car to move. Example. Car A waits for car B. Car B waits for car C. Car C waits for car D. Car D waits for car A. None of the cars can move. Traffic is completely stuck. This is exactly how a deadlock works in computing. Problems caused by deadlocks. Deadlocks can cause serious issues. Cross-mark programs freeze. Cross-mark system resources remain locked. Cross-mark applications stop responding. Cross-mark performance decreases. In large systems, deadlocks can affect entire services or servers. How to prevent deadlocks. Developers can prevent deadlocks using several techniques. 1. Lock ordering. Always acquire resources in the same order. Example. Lock 1 means lock 2. Never change the order. 2. Timeout mechanisms. Threads stop waiting after a certain time. 3. Avoid nested locks. Minimize locking multiple resources simultaneously. 4. Deadlock detection. Some systems detect deadlocks and terminate one of the tasks. Deadlock versus starvation. Feature deadlock starvation. Definition: tasks wait forever, task never gets resources. Cause circular waiting, resource scheduling issue. Result: system stops progressing, some tasks delayed indefinitely. Deadlock stops all involved tasks, while starvation affects specific tasks. Where deadlocks occur. Deadlocks often occur in systems that use shared resources. Operating systems, database systems, multi-threaded programs, distributed systems. Network services. Examples. Database transactions waiting for locks. Threads waiting for shared resources. Processes competing for system resources. Simple definition. Deadlock. A situation where two or more tasks wait indefinitely for each other to release resources. Final summary. Deadlocks occur when tasks become stuck waiting for each other's resources. This usually happens when checkmark multiple threads use shared resources. Checkmark resources are locked in conflicting order. Checkmark circular waiting occurs. To prevent deadlocks, developers must checkmark use consistent locking order. Checkmark avoid unnecessary locks. Checkmark implement timeout or detection mechanisms. Understanding deadlocks is essential for building reliable multithreaded and concurrent systems.